Thank you, Jeremiah, for the kind intro. Hi everyone, my name is Bassem, and this is actually my first conference talk, so I might be a little bit nervous. So today's topic is embedded development made easy, and the target from this talk is to approach people who want to create embedded platform for first time, and how can you use open source for that. A little bit about me. I'm a system architect, and I have 13 years of experience in embedded systems, IoT, and connected products and software-defined products. I've worked across multiple industry domains like automotive, electric mobility, and smart connected devices. And in my career, I have extensively used embedded open source and commercial platforms. So I know one thing or two about embedded platforms and open source platforms. Right now, I'm a freelancer, and I work basically with manufacturers to help them with software-defined products and open source platforms. So why is selecting the right platform is very important for you as a device creator or a manufacturer? The reason is basically engineering is a balancing act, how to deliver feature scope and lowest cost, and offer best quality, and to try to balance between these things and trade off one for another. Modern software is very rich and very complex, and trying to manage this complexity is what platforms or embedded platforms try to do. How to encapsulate, how to contain complexity and features into a backbone and manage them. And this presentation will try to approach startups trying to get started, or a device creator trying to decide what should I choose for my product, and anyone feeling stuck with locked-in vendors or suppliers who are not trying them. So when designing an embedded product, the first question that comes to one mind is, should I use real-time operating system, or should I go with full-blown operating system, something like Linux? And should I choose an application processor or a microcontroller? And if I choose one or another, so what open source platform can I leverage for my product or device? So what is the modern expectations for an embedded product, and what is the challenges and what to consider, and how can I reuse open source to solve for these things? At the end of today also, I'll try to offer a blueprint or a map of open source projects of interest that was very useful in the past in the products. So currently the most hottest platforms, open source platforms in the market, is both Yocto Linux and Zephyr RTOS. And the reason they are very hot right now is because they have a very, very strong community, and they are very well backed by corporates. So Intel, Wind River, other silicon vendors like NXP, STM, they all try to support their silicon inside Zephyr and inside Yocto. And whenever a new board or a chip is available, highly likely they will try to add the support in Zephyr or Yocto to get more market adoption for the board or silicon. And it's one way also to try to offer value for the manufacturer when they select their solution. There's a lot of text on the slides. I don't really expect us to read it, but what is the purpose of the slide is to show that both platforms are basically two sides to the same coin, and they try to offer a layered architecture. And the reason that's really nice for platforms in general is you try to contain the change in one layer, and the affect the upper or near layer. And instead of changing the entire stack whenever one layer changes, you contain the change in one layer. In practice, what this benefits us is if we want to support multiple hardware for the same software stack, it's easy to take the purple layer, hardware abstraction layer, and replace it per board. So a hardware abstraction layer is a way in software to describe hardware and try to abstract the device configuration, what CPU architecture are you using, what peripheral connected to it. And this is very useful for embedded application developers because in a sense they can write their embedded application once and they can deploy it on multiple boards. Or a middleware developer, some vendor like firm update, over-the-air updates vendor or cloud connectivity client. So you could also develop against a stable operating system APIs. And both middleware services and Zephyr services, they offer a stable uniform APIs that's nice to develop against it. So the next thing after looking at Zephyr and Yocto as a software platform is to look into the hardware or the silicon where you want to run your software. And traditionally, you get microcontroller and application processor. But nowadays, it's not as easy to say one or the other. It became more of a spectrum of compute. So on the left side, you can see that we still have the microcontrollers, but they target more low power and they run cooler, so they don't need really special thermal solution. And on the other side, they trade off compute performance. On the right side, we get high compute power, high power consumption, but they run hotter and they require sometimes active cooling solution or some thermal solution. In the mix, that's a new area where we get a high performance microcontrollers, so they have much more higher clock speeds and they get more memory footprint. And moreover, they get hardware acceleration like 2.5D graphics acceleration or camera interfaces or multi-channel audio. And you can find, and nowadays you don't really need a full Linux system to run multimedia systems. You could use microcontrollers, high-performance microcontrollers for that. Moreover, you could have heterogeneous embedded solutions where you could combine both low-power microcontroller and application processor and divide the compute based on the use cases. So for in automotive, for example, they use this if the car is parked, you don't want power-hungry application processor running. You could leave a low-power microcontroller running that doesn't drain the car battery. Or in case of smart watches, for example, you could have low-power microcontroller and a high-power microcontroller. So for a smartwatch, if you're not running or performing any rigorous sport activity, you basically use it as a watch with time and some notification. So in that case, you could use a low-power microcontroller. But if you're doing a sport activity, maybe you want to run a heavy machine learning algorithms on the high-power microcontroller, and you could turn it on instead. So there's a lot of solutions for silicons that could cater basically to whatever use case for you. And the most important aspect is when you select a silicon or a board or a chipset is to try to find if the silicon vendor will support Zephyr or Yocto, because in a sense that would save you a lot of time to spend it on bring up, and it will enable you to prototype faster or start developing your application faster rather than working on spending a lot of effort and time on low-level bring up. So the next 3 slides is a comparison between Yocto and Zephyr. They both share a lot of similarities, but they also differ in things. So Yocto is targeted more toward high power or more powerful processors. something like a Cortex-A or x86 processor. And Yocto basically acts as a build system for Linux distros. So the smallest unit that you can encapsulate to build is called a recipe. And a logical group of recipes can be encapsulated in a layer. In Yocto, they call it a meta layer. And in Yocto, you can specify your system basically with manifest that controls different meta layers. And you use a repo tool to say, I want which layers at which versions, and you can control your reproducible builds in that way. And after fetching your sources with repo tool, or the layers and the sources contained in them with repo tool, you use BigBake to build it. On the right side, Zephyr, on the other hand, is focused on simple functions and resource-constrained devices. It can run also on application processors, but the main focus of it is real-time operating system and simple use cases around it, and having a tighter time constraints around real-time. And it's quite useful on microcontroller like a Cortex-M, for example. And similar to Yocto, it uses West to fetch sources that contain the modules and use West to build, flash, and debug, and produce binaries pretty much. Both platforms can be very highly customized and very easy tailored. And the way to do this is to use device tree. So a device tree is a hardware description. You describe your hardware in form of structures, and each structure could represent hardware node and what peripheral connects it to it. You could also use kernel config or kconfig to describe what kernel modules on Linux to include in the image, or you could describe what modules you include in the Zephyr image. So they are very similar on how you tailor and do things. Runtime-wise, Yocto offers different way to encapsulate a software function. They use a separate processes for each logical group of functions, and each process has its own separate memory space, and they rely on systemd as an init process to decide which process to start first and which sequence it should start at, what they call boot target. And an advantage of Yocto is, since each process has its own separate memory space and separate process control, if it crashes, you could easily restart it from systemd again, and you could recover the function without rebooting the entire system. On Zephyr, on the other hand, it's a monolith. So both application and kernel is running in the same process, and it divides the function into threads. But on the other side, if you crash a thread, you basically take down the entire operating system and the application. Due to how Zephyr is minimally designed or have minimal by design and doesn't try to fork so many processes, it has much more impressive boot time in terms of milliseconds compared to Linux that can take many seconds to boot to something useful that you could use. Modern expectation. Modern expectations is what we're going to talk about. What is the modern expectations of an embedded platform, and how both Yocto and Zephyr try to cater to this. So nowadays there is a trendy term called software-defined products, but what does that really mean is you decouple your application features, roll out from whatever hardware you have right now. So you could come up with a new use cases, or you try to comply with market regulation later on after you launch the product, or you try to find a new competition age that you could roll out. And what companies in reality use this for is, instead of launching full-blown products, they could launch a minimal viable product and try to sell it and get some profits and revenue from it to subsidize the next rollout feature set. So that, in a sense, they use the consumer money to invest in the next set of features after the product proves its growth and that there is a market demand for it, pretty much. So both Yocto and Zephyr helps here by offering a way to decouple the application features from whatever hardware using the layered approach that I showed before. And they both offer a way to structure functions that you could scale new functions in the system without having to change the entire stack. So in Yocto, you could add a new processes to add a new function. Say, let's say it's a new machine learning model that you figured out, and you could use RPM packaging or Debian packaging to deploy it. And you could use a Vota solution like perhaps Mender to be able to download and install a new package. Or if you want, you could even use U-boot to install a full system package. Zephyr, on the other hand, offers a threads, and you could add new threads to add a new function to the user. Say you could, if you want to add a new watch app or a new function in on your smart home device, you could basically add it in a new thread, but that would require, of course, installing a full system image. Recently, Zephyr have been offering something called linkable Lodal extension, so you could actually encapsulate your function into a library, and in runtime, you could unload or reload a library from Zephyr to change or update a function without having to reboot the entire thing. Both platforms also try to cater to continuous security and regulations. So they will be talking a lot about Cyber Resilience Act. And sure, it wouldn't do the audit for your application code, but it will get you 80% there. Both Yocto and Zephyr, they offer a ways to automatically generate software bill of material when you build them for the modules. And part of the software bill of material offer you the versions of the module that you have been using, and it can offer you a way to track what CVEs associated with each module or package or source package that you have used in your build system. Zephyr, for example, it actually tracks and publishes the CVEs, so they act as a CVE authority themselves, which is quite useful. Both Yocto and Zephyr have a really nice security design or guidelines that they promote for secure design. So for example, you could find in Yocto meta security, and you could find guides on how to create and sign images to verify that it came from authentic source. There's guides on how to use secure storage, protect data at rest and data in transit. Zephyr, for example, supports lightweight M2M and MQTT and offer ways to encrypt the data being transferred to the servers. And both MCU boot in Zephyr and U-boot in Yocto, the bootloader, it offers mechanisms for secure boot and signing the image and verifying it came from authentic source. Both systems, they offer ways to create automated testing. So in Yocto, you could have a QEMU, which is an emulation image to spin up your test image, and you could build your image toward an emulation target and test your application and middleware protocol. Zephyr, it offers both QEMU and native SEM, so you could build for your a simulation for your local native machine. And there is ways to actually instrument this using West and BigBake as part of the build process. Another modern expectation is to have a continuous integration and deployment pipeline, and basically if you use something like Jenkins, you could wrap around BigBake or West to create a reproducible build, run tests, create software bill of material, run a CVE scanner on whatever version you get in the bill of material, sign image, run simulations on target, or run hardware in loop if you're a big corporate and have a device farm. And finally, upload binaries to Artifactories. IoT connectivity, there is both clients for both systems in terms of lightweight M2M and MQTT. MQTT is widely adopted, and there is a really nice solutions on both client side and server side. Since lightweight M2M is a new IoT protocol, it might not have good enough server-side solutions. But on the client side, the Zephyr implementation is quite solid, and there is also Linux client for lightweight M2M. I find personally lightweight M2M is more superior to MQTT, and that's because it's not just a protocol, but it's more like a data model and methods or remote function models. So it offers a mechanism for device onboarding and configuration at the factory, or it offers mechanisms to commission, decommission device, software updates on how to remote factory the device. And moreover, it actually, manufacturers try to contribute their device data model for maximum interoperability. So for example, if you're creating e-bike or a battery management system, you basically can reuse someone else's data model for their product and append and add to it. So it takes a lot, it's easy to create a data model yourself for sure, but it takes quite a lot of effort to harden a data model, a good data model, and a good remote functions model. And if you get this as an open source out of the box, it saves you a lot of time and a lot of effort. And both the protocol and the object registry for all this data is open source and available. Next modern expectations is delightful user interfaces. Many embedded devices nowadays expect to have a really nice UIs, and nowadays you could also have on the microcontroller side a very nice graphics with 2.5D, so you could have fancy animation to rotate the image or rotate the elements and have a very smooth interaction with it. You could have themes and fonts. An open source solution for this, LVGL, is really getting hot right now, and everyone likes it. And there is also Qt for MCU on the Zephyr side. On the Linux side, Flutter and Qt is also very nice options. And there is direct integration for Yocto also with MetaQt 6 and MetaFlutter. Another modern expectation is if you want to run machine learning on edge devices, Yocto have also integration to work TensorFlow, Onyx, and PyTorch. Zephyr, it supports TensorFlow Lite, and they actually have samples directly in the Zephyr repo for running something like a magic wand. And TensorFlow Lite is very light on memory, so you could definitely create a very nice ideas for machine learning from the sensors. So next section is challenges and considerations. So if you're designing a product, what should you think about to balance, or what should you consider before committing to one or the other, and before selecting a silicon footprint for your product? So as I mentioned at the beginning, product requirements is a balancing act. You always have to trade off something to get something. There is nothing that you would get it all at the same time. So you have to think about what power consumption budget you have, how much compute you need, how much thermal headroom in the enclosure you can have. Do you have like a direct sunlight on the enclosure? Or do you have engine running close by? What happens if you leave the device out of the sun? And do you have a throttling mechanism, how it would affect the safety of the product if it can't compute or respond fast enough? And what would be the cost if you go for a high compute, high memory, for example? Does it affect the device or the product being sold to be affordable and create a good market share for you or a market segment for you? But on the other hand, if you trade off the price and go for high compute and high memory budget or footprint, you could actually leave the device in the market for much longer time, and you could basically capitalize on the software-defined product principle to roll out feature and keep the product in the market for a lot of years. In a sense, it will lower the e-waste and it will decrease the total cost of ownership if you can leave the device in the market and you don't have to always create new generations. But it will increase the price of you have to trade off the price of the product at the end. When you create a product, it's very exciting to create a product and plan the product, but you also have to consider the end of life of the product and plan to it. So if you plan 10 or 15 years for the product, you have to have a commitment from the silicon vendor how long they will support Yocto or Zephyr for the life of the product. What would be their update cadence? What would be their security updates? Or if the CVE discovered, what would be the response window between something is discovered and then releasing the fix? And if the silicon vendors doesn't really want to do that and you want to do it yourself as a manufacturer, then you have to check that the silicon vendor doesn't have binary blobs or combined code, and they are willing actually to share the code so you can do that. There is no luxury nowadays with the Cyber Resilience Act on the manufacturer that you could just launch the product and forget about it. You have to take ownership of the whole life cycle of the product. I see my time is running up, so I might skip some of it. But this is a really nice slide because it says that 80% of platform functionality is usually something that is not differentiating. So for example, if you have a device connects to cloud, or if you have a device that can render an object or schedule tasks, that's not something that's not differentiating and doesn't add value to the user. But 20% of what add value in the platform as a source code is what you try to code to create a new innovation or a new secret sauce or a new use case that benefits the user. So this is called the 80-20% rule. And both Yocto and Zephyr can let you own the 20% and reuse 80% for free. What Yocto and Zephyr doesn't really offer out of the box is it's not going to give you functional safety for the entire product. You still have to do work yourself. You have to do the hazard and risk assessment. You have to take care of your safety requirement and do like traceability throughout the product life cycle of how you treat the safety requirement. It's not going to verify how deterministic is your real-time requirement being executed and what is the jitter next time you try to execute them. And Zephyr actually had a nice functional safety group and they tried to do a lot of work, but again, it might be for the operating system, not the holistic product. You still have to do effort to commercialize that. There are other things also, like a factory. It doesn't help you in a sense. It's not gonna give you a software download standard of operation at the factory. How do you provision secrets when it comes to communicating with the cloud certifications, for example? You still have to come up with mechanism or standard of operation to do that. And you still need developers, of course, to work on integration effort and configuration of these platforms according to your need. And this is the last slide, and it's basically a summary and conclusion. So what you see here is basically an ecosystem for open source. If you want to try to create a device today, you could basically check what technology vendors or components are here and try to basically evaluate them if they satisfy your product use cases or not. So it's a good head start. The open source ecosystem is quite strong. It will give you 80% of the functions for free, and it will get you a head started quite fast. And many of the components that's mentioned here is have an easy way to integrate in Zephyr or Yocto. So basically, it's manifest lines that you add, and then you get the sources, and it's easy to configure and build. And in conclusion, also selecting silicon vendors that commits to years of security updates and support Zephyr or Yocto out of the box will save you a lot of headache and will save you a lot of effort, and your product budget will be invested on developing your special hot sauce or special sauce or products that add value to the user, feature add value to the user. And
thank you very much, Bassem.
Thank you.
We are a little bit over time, but why don't we take one question, and would you be able to answer questions after? Maybe we can do it in the lobby, because I think things are going to start closing down. Hikmat.
Thank you very much for the overview. Like one specific question I have, let's suppose I already, for some other reason, decide on that I will have an application processor, the full feature. Is there any advantage of me still running Zephyr or any other cost versus like the full-blown operating system? Maybe like does FreeRTOS will offer like better performance or less thing?
There is a real-time in Linux now, so they actually merged real-time options in Linux, and you can do preemptive tasks or preemptive processes scheduling in Linux. But Zephyr still is created from the beginning around real-time and is created to be minimal and to run much lower footprint compared to running Linux. And in a sense, if you have a startup requirement that you need to get to, let's say, a camera processing or audio processing quite fast, Linux takes a very long time to boot from scratch, do something useful, but you could get Zephyr to boot in milliseconds, and you could even restart it and crash it and get it back up in milliseconds. Linux doesn't do that. It's highly complex to create a memory space per process and fork a lot of processes to do many things and communicate between them.
Thank you.
It's also a cost issue, right? So like a CPU versus an MCU is a significant cost difference.
Correct. At the scale, the money you save per microcontroller or compute is huge and can be quite big if you produce millions of devices as well.
But to follow up, what about like, like developing costs? Is Zephyr harder because like I'm a Linux person, like it's very easy to develop on Linux even if it's embedded because it's still familiar, whereas the Zephyr might feel like a bit overwhelming like to do it for cost.
The Linux development, if it's on application level, I agree you could use Python and you could use Go, for example, which can be easier for new developers. And I agree C language is much harder to be proficient at. it's a trade-off as well. Sure, developers on embedded on that low level is more harder to find and allocate. Absolutely, everything is a trade-off.
Thank you.